As Stacy said, my name is Jennifer Allen. I teach here at Western in the Computer Science and Business Information Systems area. I have a couple folks joining me today, a couple wonderful people from IT, and hopefully Bill Formanek will drop by and visit with us for a few minutes. So as it also says, Stacy mentioned Carla's not able to be here today, but her topic for this colloquium is thinking computationally. What is it and how can it be used? So the first thing that we're going to do is watch a video Carla chose for you guys to see today. And I will play that really quick. Learn a little bit about what computational thinking is. Okay, now you have a little bit of an idea of what we're going to talk about today, which is computational thinking and using your critical thinking skills and the world of technology around us to make decisions and problem solve, which is pretty exciting, don't you guys think? Thumbs up? The front row thinks so. All right, let's see. So just a quick overview from the video. Computational thinking, problem solving process includes a number of characteristics and dispositions. essential to the development of computer applications, but it's useful in all disciplines, including humanities, math, science, and art. How many humanities majors in here? Math majors? Science majors? Some art majors? How many of you don't know what you want to be when you grow up? No, some of you aren't raising your hands at all. Well, one way or another, we're going to be using technology in every aspect of our lives, especially, in the next 50 years. Okay? If you think about your device and what you use it for now, we talked about in my computer information systems class this morning, the digital convergence. One device does everything for you. Okay? And the video pointed out you can snap a lens on your camera and use it like a microscope, right? So cool stuff that we're able to use to solve problems and be computer thinkers, right? Students who learn computational thinking across the curriculum begin to see the relationship between academic subjects as well as life inside and outside the classroom. So moving on, here's a couple of the elements of computational thinking. We have decomposition, pattern recognition, abstraction, and algorithm design. And these are just some of the things that you do when you're a problem solver and you're using computational thinking. So let's look at decomposition. What does that mean? Breaking down data, processes, or problems into smaller, manageable parts. How many of you do that? When you're writing a paper, you're doing a chem lab, right? Building a website, okay? You're doing that. Pattern recognition, observing patterns, trends, and irregularities in data. Any business majors out there, marketing people? What are you looking at data for? Looking at patterns, right? That kind of thing. Abstraction, identifying general principles that generate the patterns. And then algorithm design, developing step-by-step instructions for solving this and similar problems. Okay? We do that on a daily basis, especially in education, right? Okay? All right. So to get you thinking, okay, so how do I apply computational thinking exactly? This is about computer science. Okay, I teach in the computer science area. Breaking a problem into parts or steps. For example, in the computer science area, we break a computational graph problem into 4 sections, each one to be completed by a different processor. What do we call that, CIS students? Yeah? All right? Our processors can break jobs into separate parts and bring it back together. Okay? And that's what makes processors in computers so much faster. Recognize and find patterns or trends. In computer science, visualize data, comparing microchip material and computer speed to notice a trend. Developing instructions to solve a problem or steps for a task. Write a computer program that sorts data, as an example. Generalizing patterns and trends into rules, principles, or insights. In computer science, you could realize complex data structures requiring less code than complex programming. That's something these smart IT folks in the front row know a little bit more about here. All right? Let's look at these on a more all-discipline perspective. So break a problem into parts or steps in literature. Lots of you are taking English classes, right? Break down the analysis of a poem into analysis of meter, rhyme, imagery, structure, tone, diction, and meaning. Okay? How many of you have to analyze Edgar Allan Poe's, what is it? What is it?
I was going to say The Raven.
The Raven, or yeah, Fire and Ice, or all those poems out there. You have to sit down and analyze, right? How do you do that? Where do you start? You break that problem down into pieces, right? Let's get the second one. Recognize and find patterns or trends. Economics. Any business majors out there? You have to take econ. Find cycle patterns in the rise and drop of the country's economy. Okay? You're using computational thinking to do those things. Develop instructions to solve a problem or steps for a task in the culinary arts. Write a recipe for others to use. Thinking of the process of making a recipe step by step. What ingredients need to use? What do you do first, second, third, fourth? If you mess up the steps, what happens to your recipe? Okay? So you're using computational thinking there as well. Next one, generalize patterns and trends into rules, principles, or insights. In chemistry, determine the rules for chemical bonding and interactions. Okay? My kid's a 9th grader in high school. He's doing this. He was doing this for homework over the weekend. Okay? Breaking things down and figuring out what are the molecules, what are the parts, you put them together, what do you get? Okay? You're using computational thinking there for sure. Let's see. Some examples. Let's see. Oh, messed my slides up a little bit. This is an example that Carla was going to use in her presentation today. I wanted to share that with you because it's a great example. She was asked by Sweetwater BOCES to help automate their summer registration program. Those of you might not know about it, but maybe you participated in a summer program through BOCES. And for a long time, they used paper and pencil to register their students. And it is such a big deal here in Rock Springs with the classes they offer during the summer. People camp out the night before so that they can make sure they get their kids in the classes that they want them to get in. Okay? So it's a big deal. And the process is pretty tedious, and they wanted to get people in and out the door faster. So they asked Carla to come up with a database. How does she do that? Computational thinking. She sat down and went through some steps. What equipment's available? Okay, that's the first thing she needed to know. You know, what equipment is available to me to be able to actually have an on-site summer registration program that's automated. Determine what systems and servers are available. Who are the folks that need the information? Who are the people on campus she would need to work with to make sure that this process happens? IT, and an organization for personal data. What information do they have? Is it electronic or is it on paper? What forms will be used for the registration process? Number 5, what software is available? Is it on machines that everybody's going to be using? Can they use our computer lab that has the internet access on every machine, or is it going to be a lab where there's only, a Word program? Okay. Number 6, how much do you know about the system you're using? And will you need to be trained on it? What about the people helping her run it once it's set up? Will they need training? What data is required for the system? For example, event information, participant information. What do you need to keep track of to build this database? Okay? She needs to know who's the parent, who's the student, what classes do they want, how much are they going to pay, when are the classes going to be held, and where? Those kinds of things. Number 8, configure and implement the new system. How much time will it take to build it and implement it? And then again, train your people to use it. Run a test pilot of your program. Does it work? I was part of that when she first came up with it. She said, hey, let's register your kid for some summer classes. And my kiddo was a guinea pig for that project. All right, number 10, check and recheck the program. Make modifications. So I think, is she on like her 6th year doing this or something with this database? So it's pretty amazing. And over the years, things come up. She makes changes to make it better for the next summer. Okay? Can you see the steps? Breaking it down. Computational thinking. We do this pretty much every day, don't we? But now we're starting to use technology to help us make it happen. All right? Examples for me personally in my classes, I teach an Intro to Information Management course. And in that course, my students are required to build a website. First thing we do, first of all, think of a topic. Okay? And then I have them fill out a website design form where they have to start thinking about the content and breaking it up into different pages. What is the kind of content that they're going to have? What's the website layout going to like? Building a tree diagram and then actually putting it into the computer, building the website using the technology. So there's another simple example of how to use computational thinking in what we do every day. Okay? All right, so now I'm going to introduce Bill.
Well, you're going to introduce Carrie.
Oh, you want Carrie or Kit first? All right, I think Carrie's ready.
All right.
So this is Carrie Piazza. I'm going to trade her microphones. And she is our lead computer support tech here at Western in the Information Technology Department.
Well, so I'm Carrie, and I'm with Information Technology here on campus. And we're pretty much every part of our life is computational thinking. So I really didn't break this down like she just did in the slide for you, so you don't get the nice presentation like me. But information technology services, what is it? Some people don't even really know. It transfers, anything that transfers data or information, IT is involved with it. I'll get into that later. So information technology facilitates the use of technology and information for the end users. So if your devices transfer the data, we'll probably end up helping you with it at some point or another, or somebody in IT has done something to make it work for you. So there's all kinds of areas in the IT fields. There's enterprise architecture, that's designing and architecting a company or an organization's architecture for IT and how they're going to build it and handle it. You got network services, wireless services, there's server farms, server administrators, there's virtual services, a lot of virtual servers out there, cybersecurity and security services, telephones, cell phones, mobile devices, you name it. This is just some of the stuff that IT touches. I used to work at a transportation department, and all of our signals and we had cameras on the roadside. They're all transferred by wireless satellite. They all came back to IT, and we were in charge of it. So there's a lot of thinking involved. Oh my God, I have too much stuff here. So we also do physical and hardware troubleshooting and building. We do applications and specialty software, web development, database applications, data analyzing, and technical support. So this is just a few of the areas, and so as you can imagine, there's a lot of analyzing that we have to do and try to figure out. And there's no possible way that we can have all the answers. So we have to do a lot of thinking. Oh boy. So these are some of the different careers that are in IT fields. This is just a small assortment of them, but there's IT directors and technology officers, network engineers, system analysts, server administrators, database administrators, programmers, web developers, project management, computer science specialists. There's technicians that fix things, help desk, they get you to the right area. People do consulting, they train on IT. Just a lot of things that can be done with this. Anyhow, so the most important skills, besides being technical and knowing how to do all the information, I'm sorry, you guys, I'm terrible at this. Anyhow, gotta have good communication. Apparently, I don't have it in a group of people, but when we're by ourselves, we're okay. Teamwork, you have to work with everybody in every field. No matter what, you're always going to be working with somebody, and the end user is really important too, because they, can you hear me okay, Eric? No? Without that teamwork and communication, a lot of times things fall apart, and with IT, there's just so many areas that things can go bad or go wrong that you really have to have good relationships. You have to be able to think analytical, you have to be able to communicate, you have to come up with different ways of doing things that are out of the box. You have to be really good at doing time management and project management, because there's a lot of areas that touch each other. You have to have a lot of versatility, and a lot of people have certifications and degrees. I myself, am a hands-on person, I've learned that way. In today's world, there's all the degrees and certifications. Yes, that's all. All I have. Which one?
Do A204 since you just did that.
Oh, well, yeah. So Eric and I, A204 is a classroom over in the annex building, and we were asked to replace the technology in there because the projectors were too close. They needed to have HDMI. They wanted a new computer, bigger monitors, and a new document camera. So Eric and I had to work together with teachers, instructors. We had to get into that room, order the proper products, make sure everything was going to work, and then schedule the time to go in, and did everything and got out before class started, and it was like we were never there. So in our case, no news is good news. But we had to do a lot of organizing and communication and planning and talking with each other, ordering the proper products, how's it going to affect what they're trying to get the students to see. So they have dual monitors, dual screens in there. It's a lot better setup for them now.
So maybe I want to use that one.
Yeah.
So part of that process, did you
You see, Kit's going to be way better. You're in for a treat.
Did you have problems when you were setting it up, and how did you handle that?
Not really. We did a lot of communicating. Did we, Eric? We have problems?
No.
We just had to locate other equipment and do some swapping out and a lot of analytical thinking and how's this going to affect things if we had to make sure we had a proper graphics card in place so that we could handle 4 connections at one time. We had the dual projectors upstairs. Any problems we ran into, we just talked about before we went in and placed it. So.
In your field, how often do you find that you run into unintended consequences?
Every day. Well, I would say it's a crapshoot. We're not in high school, right? I would say that. You don't know what you're going to get every day, so you just come in with the attitude you're here to help people. You're going to problem solve, figure out what you can do to make things better. That is pretty much what we do all day. You just find a way to make things work. You don't always have an answer for everything, but then you get asked to do these kind of things, and you're totally uncomfortable. Yeah, Kit, you could go next, Kit.
Anybody have any questions for Carrie? Other than us in the front row? Okay, thank you.
Sorry, guys.
So my name is Kit Kofod. I work in the IT department here, and I am a PC support technician. So Carla kind of came to us and gave us a general idea, not exactly what we would be talking about today, but hopefully I can thread it in. So what does it take to work in IT? Things working. First of all, IT is not magic. You don't have to have a magic wand to be able to do it, and you are certainly not a wizard. However, the people you're working for and helping, they often think you are, and they think you do have a magic wand that can just miraculously do whatever needs to be done. But as Carrie just told you, there's lots of things that go on behind. What do technicians do? We provide assistance for any kind of technical hardware or software issues. Things from slow performance on any kind of equipment, any kind of connectivity issues, and end users' access to data, which is huge now, and it's a growing field, obviously, because we have more and more information just growing exponentially out there that we want to link to, we need to have access to. Users need it, you need it as students. We do installation and setups, we provide maintenance on all the equipment that we supply here, and we're troubleshooting all technology all the time. It doesn't matter if it's a PC, a laptop, a printer, a projector, a camera, a phone, somebody bringing in their own device. It doesn't matter if you're a student, an instructor, or a community member, because we're helping anybody that comes into this building. And bring your own device right here is happening more and more, and that's a challenge to try and think about everything that you need to support anyone's device that they're bringing in and make sure that it's going to work for them no matter what they want to do on your system. So you can tell it starts to get a little more complicated. The first thing I wanted to talk about in IT is like soft skills, because you pretty much are the PR for your department. You are the first line, and you need to have good customer service skills. People, when they come to you, they may be at their very worst, so you have to be able to handle that. You have to be able to redirect, because they may be mad. They may just be mean to you, and you can't take that personally. It's not about you. It's about the frustration that they're having with whatever is going on, with the piece of equipment or with not being able to get to the data in a timely fashion, right? So patience is huge at the support level. You have to be able to listen to them for what is actually going on, because sometimes what they're telling you is not really the technical issue they're facing, but it informs you and it tells you what they're needing to do with that, perhaps. So, and you need to walk through and get them there. Gauging their interest level, I put that on there because it's often In technology, we get really excited about what we're doing and what's going on, and oh my gosh, I solved it. You know, I should get a good gold star on the forehead. Yay! But sometimes they don't really care. They just want their thing fixed, or they want to get to the information. They don't want to know how or why you did it. So often gauging their interest in it will determine how you report back to them. Yes, I solved your problem, you're good to go. If that statement is good, or you need to break it down so that they don't do it again, because part of your job is educating, and we'll get there too. Everyone is your customer. So Carrie is also my customer as a coworker. I support all of my coworkers from the help desk position all the way up to our IT director. So everyone is a customer. Don't discount anybody. Okay. So what kind of job skills do you need to have? Problem solving is huge, obviously. That is what we're doing all day long. But what's interesting for me is not often, it is determining these two things. Sometimes it's more important to know what the problem is not than to know what the problem is. And having a set way of thinking when you're going into something doesn't help you solve the problem. So, problem solving, all the time, you are educating yourself and you're educating the person you're working with. Maybe it's something they're doing all the time. You can teach them how to not do it or to do it a different way that's more efficient, that maybe doesn't cause that problem over time. You're answering questions, and that's vital in understanding what the problem is listening to them, asking questions of them, and also them listening to you, right? So you can meet in the middle there. Troubleshooting. You have to use all of your knowledge to find out what the problem is. What should it be doing? What is it doing now? Right? Are there recognizable patterns there? Am I seeing the same thing over and over? Are there logs that show me if a pattern is happening? Am I getting that same error all the time? What is that exact error? What does it affect? You have to start small and decide to start somewhere with a problem. You just have to start somewhere. Sometimes it's addressing the most critical concern that your end user has and starting at that point. If you can get there, the core of the problem. But you have to do one thing at a time. Sometimes you get into it and you're going, wow, it really sounds like this. So this is kind of where I think I want to start. And you start dissecting and pulling apart your problem and realizing the scope of that problem is way bigger. For instance, we are just having this kind of experience here. There's been some connectivity issues around campus. And it's due to our antivirus software, right? But as we've gone to different areas in the building and weeding out what is the pattern that I see, where am I seeing it, how often do I see it, what time of day am I seeing it, what programs is it affecting? I mean, it gets larger and larger. So trial and error is a kind of problem solving. And we use it a lot in IT, but we also use logic and reasoning. You know, if I do X, what happens? Then Y. What if I don't do X? What kind of Y things are happening for me? If I choose not to address that, does it get worse and worse and worse and build up over time, or am I getting the same exact thing each and every time? How do I prevent or make things more efficient? And that's Carrie's job. So are there ways to automate processes? That's also Carrie's job, and she's working on a lovely server that I'm just dying to have that will help my job immensely. It is called System Center, and it is, can you tell us a little bit about that? I'm going to get close to you.
I get to talk into you.
Yeah.
Well, System Center is basically a server that allows us to push applications, updates, we can set policies, and we can do anything we want from a server, and it'll push it out to all the clients at one time, or at specific times whenever we determine. But then we don't have to have an individual technicians go to every computer on campus. We have hundreds of computers around here. We can more automate things, so it'll make our life a lot easier down the road.
Less footwork. Woo! Okay. I get it back on. Okay. A big thing that we have to be able to do is follow directions, not just the ones that you create, but the ones given to you by your peers or areas. Because sometimes we go into a lab, and that lab has a specific set of rules that we have to do things by before we can start addressing a problem. Even we should be wearing our eye protection when we go somewhere, right? So I think the biggest thing about IT that's fun for me is that everything always is different. Everything changes every day. What you think you solved yesterday, you can't use those same tools today to solve something often. So it's starting fresh and thinking new, and it is being creative. If you can approach things with curiosity, you can solve the problem. In IT, you have to love to learn because you're learning something new every day, hopefully. You have to be organized so you're able to handle many jobs or many things at one time in your day. Time management is very important. Carrie is the queen of documentation, and I love her for that. To document processes and actions so that when somebody else goes in to that room or that software or that piece of equipment, they have a set of steps they can follow to try and do the installation, to remove, and to troubleshoot. Be resourceful. This is also one of my favorite topics of all times in resourcing. You have to know when to ask for help. You're not ever going to know all the answers. And if you were never perfect in IT, you're going to mess up. You're going to take things offline and take the system off. Willing to fail is huge in this field because this is how the learning happens. If you haven't broken it, then you really don't know how it works. Breaking things and putting it back together is really, really important. And that's where computational thinking, you guys do it all the time without a label on it. If we didn't label that, you were doing it all the time, every day, with everything. So, yay, that's my spiel. Anybody have questions? Great.
Well, my name is Bill Formanek, and I teach economics here at the college. So I am not a technical expert like Carrie or Kit or Jen or Carla or people in that field, okay? But prior to teaching, I'll give you a couple of quickie life stories. This is my 9th year teaching. My 2nd year teaching here at Western. I also taught at a college, 2 colleges in Florida for a couple years before coming here. I also taught for 3 years in the K through 12 system, and I also taught for about 3 years out in industry. So teaching, if you will, is a second career for me. I spent roughly 25 years, I'm not that old, am I? I spent 25 years out in industry in management jobs, primarily in microelectronics companies, including one that Gordon Moore co-founded that you may have heard of called Intel. Okay? So I'm not here to talk about technical stuff. I will talk about why Gordon Moore has a law named after him. Okay? And it's pretty interesting. And I use these kinds of concepts in my job pretty much all the time. I teach economics. Okay. Before we get into economics, how many people are planning on either serving or cooking or eating a Thanksgiving dinner coming up? Raise your hands. Okay. So when you go there and the dinner's popped on the table, you say your blessing if that's what you do, and you start eating. That's a wonderful time. What goes into putting that dinner on the table? Okay, right before we start eating, somebody tell me what has to be done immediately before eating.
You have to put it on the table.
Okay? And once the food's on the table, we just start grabbing, or, oh, we need silverware and dishes. Oh, okay. Well, before the silverware and plates are put on, you used those same plates last night. Oh, they had to be run through a dishwasher. Okay, good. Well, before the food is put on the table, it has to be cooked. Maybe it has to be washed and cleaned. Maybe it has to be bought from a store. Okay, what I'm getting at here is the end result is one thing, but what about all the steps that lead up to that? That is called computational thinking. Okay? When you hear the term compute, don't necessarily think in your mind, oh my goodness, math, calculate, do some numbers. Well, that may be part of whatever it is you're trying to do sometimes, but we do many things. Am I getting out of the way, Eric? Am I okay? Okay. But what I mean to say is there's a lot of steps that go involved in the end product or end service that we don't think of, that we just do automatically. Here's an example. I worked for a company in Eugene, Oregon. It was a microelectronics company that was starting up its first plant. The company was called Hyundai. We've all heard of them. They make cars, they do shipping, they do natural gas. A huge Korean corporation. It was their first plant that they were building outside of South Korea. One of the first things I was hired to do was train our entry-level production technicians. And we had the luxury of time, as the plant was being built from the ground up, we hired the people that were going to run the equipment to make the final product. We had an arrangement made with the local community college that the people we hired to be entry-level technicians were going to go through a program that was put together for us to give people who never had a background in this line of work some rudimentary skills for technology. A little bit of chemistry, a little bit of physics, a little bit of problem solving, a little bit of electronics. So when they came to site, they'd have an idea of what the final end product is. Before they went into the factory, which we call a wafer fabrication plant, or a fab for short, I worked with these people for about 6 weeks in a group. And one of the projects I had them do as part of their training was build paper airplanes. So I came in and I had an assistant. I had her box up all the supplies they'd need, and I divided this group of about 40 or so people into probably 6 or 7 groups and told them what they're doing. We're going to spend the morning building paper airplanes. The look on their face was like, what? We're getting paid to do what? Because they were on the clock getting paid the whole time. Okay? So I told them what they had to do, and I had made a paper airplane with a few modifications, and they were allowed to look at it, and then I walked away, and each group nominated a production manager. And as the group had questions, only the production manager was allowed to come see me and to ask me questions. And I would show him or her the plane. They only had 1 minute. Okay, so what we're trying to do, this project involved communication, it involved teamwork, it involved collaboration, and the end result was which group could build the most paper airplanes according to specifications in a fixed amount of time. It was pretty competitive, okay? What was really interesting is in each box that I gave each team was a ream of paper, a couple pair of scissors, some pencils, maybe a ruler or two, some tape, everything that they would need. And I told the class as a whole, just before they started, I said, everything you need to do this is in the box. Questions? Go to it. So I didn't tell them how to organize or what to do, so I kind of let them figure it out. And after about 10 or 15 minutes, most groups are, measuring, folding, they divvied up the tasks doing it. this one group was still kind of scratching their heads, haven't done any work. So finally, the production manager came to me and said, we can't figure it out. I said, well, what's going on? He goes, well, we have scissors. There was a penny in there. I had a couple of dice. And this guy, Mike, says, we're stuck. We can't figure out, what do we use these dice for? I said, why do you need dice? He said, well, you told us everything in the box we need. I said, no. I said, everything you need is in the box. They're wasting all this time figuring out they got to use all these things. They didn't have to use them. Okay? So communication failed, and the intermediate steps of computational thinking wasn't there. It's like, I could have had a V8, you know, one of those kind of things, one of those moments. So then they got back on track. But I wanted to share that as an example that just because you have tools doesn't mean you have to use them. Okay? What is the end result? How do you step backwards and take the intermediate steps and proceed to a logical conclusion? That is computational thinking. There was no calculator, there was no number crunching, there was no calculating of things. Okay, but that's just one example. I wanted to share an example that I do use a lot teaching economics in my classes. This is called Moore's Law. Gordon Moore was a co-founder of Intel Corporation. He founded it in the mid-1960s with a gentleman named Bob Noyce. It incorporated in 1968. I worked at a brand new Intel plant that was coming online in Albuquerque, New Mexico back in the late 80s. Okay? Gordon Moore is a legendary man in the semiconductor microelectronics business. He realized that as the state of microelectronics was advancing, that the complexity and the amount of transistors that could be crammed onto a little piece of silicon microchip was doubling approximately every 18 to 24 months. So the rate of technological advancement to build integrated circuits, microchips, was advancing, and hence the computational capability and the functionality of these microchips consequently was doubling about along the same way. So when it said Moore's Law, and this paper has to do with measuring inflation and economics. One of my students gave me this, by the way. Okay, now what can we glean out of here? Well, maybe you can't read it all, and that's okay, but on the second page, for those who have not taken economics, who's heard of the term inflation? Okay, what does inflation mean? Shall I pick on any of my students in here? What is inflation, when you hear the word price inflation, what does that mean? Anybody? Something's going up in price. Okay? That's not the technical economic definition, but it's close enough. Prices are rising. Okay? Well, we know, or if you think about it, from the mid-1990s till now, for those old enough like me to remember, we didn't have these smartphones 20 years ago. A cell phone 20 years ago was about the size of this water. It was like a brick. Okay? Due to computerized functionality and shrinking things down, more and more things became micro-sized or miniaturized. Okay? Well, in addition to the science and the electrical engineering and the physics behind it, the use of these devices has made our life much easier. It's made the ability to conduct internet transactions, international trade. It's facilitated a whole bunch of things, driving economies around the world. Okay? One line in here, I'm sorry you can't read it, but there's a measure from this study that looks at inflation from about the year 2000 till now, what the rate of change of prices was in the United States over this time. And it shows that when you factor in Moore's Law, our inflation rate would be higher had it not been for the improved functionality and use of computers, word processors, computer software, and the integration and innovation that they resulted from. Now that's a little bit of a step from cooking a turkey dinner for Thanksgiving, but it's the same kind of concept. No matter what it is you study, you can use the principles of computational thinking. And whether you think about it or not, you do that every single day. Whoever, one of you ladies mentioned that. Okay? When your alarm clock goes off in the morning, until you're sitting here in this class listening to my bad jokes, a lot of things had to happen in the process. You may not have thought about them consciously, what you have to do to get to the next step. But subconsciously, your body reacted, I got to be somewhere at a certain time, I got to get dressed, I got to brush my teeth, I need my books, got to feed the dog, blah, blah, blah. All these things had to happen. You chose what you did in what order for a logical reason. And usually we can behave logically without having to think logically. But it's great when you do both. Okay? Computational thinking is I guess, a way of discipline. It's not a study. It's not a science, really, per se. It's a way of stepping through what you need to do to get from point A to point B. Okay? I do use these types of processes in my class. Let me throw one little economic example real quick. Let's say you have a midterm exam coming up in a couple of days, and you're planning on spending the next couple of nights studying for that. The night before the exam, one of your friends calls up and gets a free dinner for two at some newfangled restaurant that just opened up. There's been a waiting list to get in, and they say, hey, I got an extra ticket. Do you want to go? And you're like, oh, man, I got this test tomorrow. So you have a choice of doing option A or option B. How do you decide which one you do? Okay? Any people in here may choose different types of scenarios. The point is, according to economic fundamentals, you should do whatever gives you the greatest satisfaction, knowing there's a trade-off. If you go out to dinner, maybe the time you could have spent that you didn't study ends up costing you 5 points on the test. Or if you say, no, thanks for the dinner, I'm going to study, you get an A on the test, but your friend's like, oh, that was an amazing dinner. You made a trade-off. Okay, and that's part of computational thinking. Choosing between options logically, what your end result needs to be. If you can step things back, that's an example of computational thinking. All right, sorry I threw the economics. Every chance I get, I do that. Any questions about what I do, how I use it, or how it may fit into any of your lives? You don't have to calculate. It's computations as far as what you need to do given what you're working with. Thank you.
All right. Well, it is just about 9 minutes to 1, so thanks all of you for coming, and I hope you learned something about computational thinking today, and maybe as you go through the rest of your day, you'll think about what we talked about today and how you go about making decisions in computational thinking.